Hi guys, we are going to start our system design discussion with Uber Eats today. I have not designed the system at all, even though I work for Uber. I have never had a chance of working on Uber Eats, and so I thought this is a good opportunity for me to think about how to design the system of Uber Eats. And before we do that, I'm just going to basically put timer so that we can finish this off within 30 minutes. So let's talk about what are the key requirements of the system. So here I've written the requirements are you're to search for restaurants, you're able to order food, and then you're able to deliver the food. Now searching for restaurants and searching for food, that's a very simple thing to do. So I'm not going to focus too much on that, but I'm going to think about how can we design a system where you're able to order the food as well as get the delivery. So let's talk about who are the key um, actors in the system. So obviously you have a very important actor, which is the restaurant. So I'm just making this as a house as a restaurant. So this is your restaurant, um, which has um, which has to basically accept the orders, reject the orders, and so on and so forth. And then you have the courier. So I'm gonna make a car out of here. Say this is the courier. So this is the restaurant, this is the courier, and obviously there is this person who is our user. Bad diagrams, but you get the idea. So the user is using this app. This is our app, and it is browsing all that stuff, and then sends an order. And order is send order. An order is sent to the restaurant. The restaurant may basically take some time. There is a wait period for that, and after the restaurant basically accepts the order, so a notification goes back um, when the restaurant accepts the order, and then this user keeps on waiting. The restaurant goes into preparation, so it sends obviously the prepared food which goes into the kitchen. Now, obviously, that is something internal to restaurants, so we won't talk about that. And then once the kitchen is done, kitchen sends a message to the restaurant saying food done, and then this sends a request to a pickup request to the courier. The courier either accepts or decline, obviously. So let's say courier accepts it, um, then the courier drives towards the restaurant. The courier picks it up, and so the restaurant, and so this one sends a message saying that your your message, your thing has been picked up. Then courier starts to drive towards that, and then delivers the food. And then at the end of the day, once you're delivered, then that's when your flow ends. So as you see, there's a lot of moving parts in this. Lot of states which are being changed here, going from the order being placed. So state. If you just draw the state machine for this, which will help us in designing the system, I will actually use a different color for this. So this part of the board we will draw the state machine, and this part of the board we will use for our system design. So obviously the state machine is we will start with the state of the order or state of the request. So first request is in the you start from nothing. There is no request or no order, and then you go into a state called order placed. Okay, so from start request, this is the starting node. You go into state called order placed. This order can either be so basically you go into a search state, which is going here, and then from the search state, add to cart and all that, you come here, and this once the order is placed, um, the order is sent to the restaurant, okay, and the restaurant can either accept the order or decline the order. So let's say if the restaurant accepts the order, it's fine. Otherwise, any decline goes here. Why called. So the restaurant can either decline the food, so you go into the search state, obviously, or you go all the way to the start, or it can accept the food. And when they accept the food, then food prep. So you go into the state which is a food prep prep state, and then the food is being prepared. The app is waiting for the response, and then finally the food is ready. Um, Food is ready to be picked up. Then the food is ready to pick up, and so the food is ready here. And once the food is ready to be picked up, um, you are basically, you send a message to the courier, send pickup message, and then the courier can either accept or decline. So let's say the um, courier accepts, so declines it. So you send a message to courier 2, blah blah, until you get an acceptance, right? So finally somebody accepts it, and let's say nobody accepts it, then you send a message back to saying that you cannot accept it. Then the courier basically accepts this message, and then courier drives towards the restaurant. So basically that's the driving state, and then courier pick up food picked, and once the food is picked, the courier is again goes to a different driving state where it is, or you can say in on route. Um, this is again en route for delivery, and then finally this gets delivered. So this is delivery. This is right, okay, and that's when your state machine ends. So a lot of states being changed here. Now let's try to map into a system which would basically be able to handle the state. Um, so in terms of services, let's talk about the sizing of the system, like how large the system has to be. So let's say there are 100 million customers of Uber Eats. Okay, that's the total number of customers. And let's say 70% or 80% of these customers are ordering food every day. So that's 80 million orders per day. So in order to sustain this 80 million orders per day, what's the request per second that you would say? So 80 into 10 to the power of 6 requests per day, which will be 3600 multiplied by 24. So this is the amount of requests per second. So if you do a simple math here, let's see. Let's use a calculator. That's 80 million. So 80 divided by 24 divided by 3600. That's 9, 1, 2, 3, 4, 9, 9. So that is basically about 9 to the power of minus 4. So that gets cancelled. That's 2. That's 180. And so around 18,000 requests per second. That's what you have to basically um, that is the scale that you're talking about. So obviously there we have to have a way to horizontally scale this. So let's say you have a load balancer. That's where everything starts from. This when you place an order, a request is sent to this load balancer. Okay, and let's say the service call there is /order. Okay, that's the service call, and then this request basically um, picks up an app server. I'm going to basically make it simple. Let's say you have these app servers, and this app server gets the request, the order comes in, and then this order is now. Let's talk about the data model real quick. So the data model will obviously have a user table, which will have the user. It will have a restaurant table, which will have the restaurant as well as the menus, and then you have the order table, and the order will have um, ID is called the user ID. It's got the restaurant ID. It's got obviously the food order. So basically the cart ID, and this is, let's say this is a table called cart, where it has the order ID and all the food that you've ordered. So food ID and all that. It has the cart ID, and then this has the order state. What is the state of the order? The date it was placed, as well as the driver. Okay, driver ID. So this is the state. This is the table. Obviously, user. This is a foreign key here. Restaurant is a foreign key here, and then there is a courier table, which is nothing but a user, but we can actually have a different table for courier, which will have a foreign key. So this is the data model in a way. So when the order is placed, um, uh, we we add an entry into this table. So we create an order, and the status of the order is order placed, right? Then this basically goes and writes into, let's say, a queue. Okay, this goes and writes into a Kafka queue, and we are using a queue. Um, Basically, now we have to send a request to the restaurant, right? So then there is an ingester or a queue processor or order processor, and this basically picks up this order and then sends a notification to the restaurant. So there is maybe a notification service. Basically, this notification service, what it does is it has some mechanism of sending this notification to the restaurant, and then it um, it takes the service and then it puts into a different queue, again a Kafka queue, which is maybe a pending. Or actually, this is not. That's not right. So this goes and updates this table. So this notification service sends a notification, and then it waits for the notification, and it goes and basically updates this table. Okay? This updates this table that it changes the state from order place to the notification sent. So send notification here. Okay. Now this notification service basically keeps on waiting, and it maintains the state of that order. Now it is possible that between the time that order is accepted by the user, by the restaurant, and the order, the user um, may cancel the order, right? So it sends this notification, but the order can be cancelled. In that case, this notification service, um, we'll talk about the different. So cancellation could be a different flow. But let's say this goes and updates this table, and then the notification service waits for the restaurant. The restaurant gets the order, accepts the order, and once the so this order processor accepts the order. Sorry, this one should be here. So this is number two, and then once the order is so here it sends the order as accepts, and then it basically goes and update this again um, to so this is order placed, state number one. The restaurant is and this is the notification, state number two. Um, Basically, so and third is this order is being order has been accepted. So the order goes actually here. So this is two. I'm not able to do this here. And again, so order is processed. This notification service sends out the notification, and then order processor service waits for that. Once that is done, goes and updates the service, and then so all these orders, and so there are like multiple order processors. So this is happening in OP. So and probably multiple Kafka queues here, um, just so that you can scale the system. And the partitioning could be through the location of the user. So all the locations orders being placed in this particular zip code are going to one Kafka queue. Orders being placed in a different zip code can be in a different Kafka queue, and you can have a range of zip codes. So between zip code this and this, you're going to this Kafka queue. So you'll have to come up with some kind of partitioning scheme so that you are able to partition this data, and similarly order processor will be there. And there should be an active order processor and a passive order processor. So let's say the active order processor dies, you can pick up a new passive order, a new order processor for that particular queue, so that the orders are not going into limbo. Okay? Again, a notification service will also be multiple notification services. Then once the food is prepared, the restaurant will send here basically notify um, again. So some kind of service with which the restaurants interact with. So this is, let's say, the restaurant service. Um, so this will basically notification between so um, notify the restaurant, and the restaurant will notify the notification service. If once the food is prepared, it will basically go back into the order processing service. Okay, and again, this order processing will write the same. You will apply that. You change the state again that the order is in process. Now, whenever all these things are happening, there are notifications being sent out to the app, right? So how do we add the notifications? So this order processing service is basically um, like push notification, push notification service. So this also has a push notification service. So whenever these things are happening, this push notification service is maybe the order processing service is pushing all this notification into another queue. So this will be a notification queue, and this is the push notification service. And so this order is as the things as it's working through it, it is basically um, pushing in the notification queue, and the push notification service is pushing this thing to the user's app, saying that your order is here. So basically, this is the reason you want to do all this asynchronously is because so this order doesn't have to worry about like actually sending out a notification, because notification can be delayed, and so you don't want to kind of restrict this flow. Once the push notification is done, and then um, the order is being processed, and once the order is being processed, what will happen is that you will this order processing, now there has to be so here we are here, so the food is prepared, the food is ready to be picked up. So this restaurant sends a notification to this notification, and it goes to the order processing service. Once the food is ready to be picked up, it basically goes and calls a dispatch service. Okay, and the dispatch service is simple to that. Is that you have a service called nearby drivers. Okay, so the dispatch is going to call all the nearby drivers, and it is going to put that in this another queue, or nearby couriers, basically couriers, and assuming that there is a geolocation and everything else. So this is a queue which is the courier queue, and dispatch puts this in the queue, and then there so it is basically puts all the couriers into this queue, and then basically this dispatch processor gets thing from this queue, and it uses the or basically somehow it communicates, or it could be either it's putting in the notification queue, or maybe there is it basically sends a request to the courier. They send request to the courier. Now this dispatch processor will wait for some time. It'll do a timeout, and if let's say the courier accepts, then it'll remove the queue. If the courier does not accept, then it'll remove that driver, the courier, from that queue, and go to the next one, and next one, and next one, basically. And once the driver accepts, then the dispatch service will uh, send a notification to the restaurant service. Will notify send a notification to the restaurant service, and the restaurant service will notify the restaurant. So this is the restaurant, that the courier is on the way, as well as put put it in the dispatch queue. Right? Remember, the dispatch queue is for those. Sorry, the notification queue is for those purposes. And once the courier accepts the order, or basically picks it up, um, then again, once then the restaurant would notify, the restaurant service will again notify this, which will in turn notify the order processing service that the courier has notified. This will again go and update this database that your food has been picked up, and obviously put in the notification queue, and then the courier will be on its way. So all this is managed through this one order processing, which is the state of the system. Now you can basically, in order to reduce the I/O, this you can maintain the state in a cache. So you can have the state maintained on a Redis cluster, so that you don't have to basically work with the I/O. But when let's say the cluster dies down, or and also you have to maintain some kind of what do you call that, stickiness, because you don't want to go to a different cluster. You can probably go to the same Redis cluster based on. So you can use things like consistent hashing to maintain this, to maintain which Redis cluster. So imagine like these orders are placed in the Redis cluster. Okay, actually here I can show it on the ring. So let's say these are all Redis nodes, and let's say your order being processed on this cluster. Let's say this is order A, which is obviously being replicated to other clusters, just in case if there is an outage, and order B is replicated to other clusters. So you're always basically going to the same Redis cluster for your order processing. Obviously, this is all mapped into Cassandra also. So your Cassandra is your persistent layer, but then you also have a Redis clusters, just so that you can increase these things. So as you see, this is the main bottleneck. So you have to make sure that this table, which is being updated multiple times, is is able to scale based on the number of requests. So yeah, once the order gets picked up, and again, I'm missing a lot of things about location, about the location updates. As you know, every all when the driver is moving towards the 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 pickup area, or sorry, moving towards the user, the driver's app is constantly sending the location to the Uber app, the Uber system. I'm not going to go into that because that's something that we can tackle later on. But imagine that the app basically is sending out the notification, and the rider app is sorry the user app is getting those notifications. Um, so yeah, once the courier picks up, again goes to order processing, it'll go again change the state here that your user has been picked up. It'll basically add to the notification queue, and it'll send a push notification. It may send you a text message also, and then once the food is delivered, again the basically the driver is going to, so there is this driver app or the courier app will say the food has been delivered. It will go and contact the order processing service, and the order processing will basically go and update this again, and then send a notification that your food has been delivered, and then send the next notification. So as I said, the main crux of this whole system is maintaining the state, right? So you're going from one state to another state, and things can go wrong in any of the state. So the first thing is making sure that your state machine is highly scalable, in the sense that it is able to have good reads and writes. So we will not be using any SQL database because SQL database doesn't scale with reads and writes. So you cannot. So you need to have a NoSQL database that you're going to use. And then, as you said, you can maintain all this in a Redis cluster to mirror, but then you have a Cassandra cluster to actually do the persistence. So you write to Cassandra, and then you put it in the okay. But that is something that if you don't want to kind of do that kind of optimization, I think it is fine. But then you have to really think about the different kind of the way you scale all the requests are coming in. So you basically have to decouple the system, because at every point, if you don't decouple, if this is a coupled system, that's why the notification is completely coupled from here. That's why this whole order processing that happens in a very asynchronous way. So this order processing this order processing API has to be scaled. So you need to have like multiple machines using the order processing. Um, so this is one bottleneck that you will see, because a lot of requests are hitting this. This is the second bottleneck that you have to resolve. And the third is making the system as asynchronous as possible. Um, the other part of the system is how do you debug when all these things are happening. So you have to kind of maintain some kind of history or some kind of debugging information of all these API calls which are happening, where the system is actually, which state the system is in, so that you are able to identify what went wrong. Let's say the order was not delivered, or if the communication between restaurant and the courier broke down, we can do some of this. So that is how I would design the system. Again, this is probably a very very watered down version of what Uber Eats actually does in real time, in real life. I wish I worked with a team, so I would know how they actually build the system. But I think that's where uh, I would do that. So let's say, so once you build the system, always go back to to the drawing board, saying, have you figured out the requirements? If the requirements are search for restaurant, yes, you are able to do that. You were able to order food through this mechanism. You were able to get the food delivered. That is, and then it talks about different actors in the system. So that's Uber Eats, and I hope this was helpful a little bit. And that's it. Thank you, guys.